Hi, and thanks for joining this brief overview of our work, TapTrap, animation-driven Tapjacking on Android. I'm Philipp, and I'm a PhD student at TU Wien, and this is a joint work with Squarcina, Sebastian Roth, and Martina Lindorfer. Without further ado, let's talk about some background. First of all, what are activities? An Android app consists of multiple activities, and you can think of an activity as basically a single screen of the UI. Consider, for example, the Contacts app. The Contacts app has an activity, people activity, that is used to display information about a specific contact. When the user clicks the Modify button, a new activity is launched, the so-called Editor activity. In this activity, the user can modify specific information about a contact. The way this launching works is by using so-called intents. The people activity will send an intent or launch an intent that targets the editor activity. The Android system will then handle this intent and will launch the corresponding activity, in this case, the editor activity. In this case here, both people activity and editor activity are part of the same app. If an activity of one app wants to launch an activity of another app, then this other app needs to be declared exported. So that means only exported activities can be launched by other apps. And all of these activities are aligned in a so-called backstack that grows upwards. Typically, the element that is on top of the backstack is the one that receives user inputs. And then there is also the concept of a task. A task is a single element in the recent app list. So how did previous Tapjacking attacks work? Assume that we have a malicious app that contains a sensitive UI element, such as this "Don't click me" button here. A malicious app can launch some kind of overlay over the victim app. As we've already heard, usually the element that is on top of the backstack is the one that receives user inputs. So in this case here, the overlay would receive user inputs. The malicious app can make this activity pass through. That means the touches pass through to the underlying layer. The goal of the malicious app now is to lure the user into tapping on the position on the screen where the sensitive UI element is placed. For example, by showing a button such as this "Click me" button here. The user clicks the "Click me" button, the touch is passed to the underlying layer and reaches the "Don't click me" button, and therefore the tap is, so to say, checked. Android has introduced several mitigations to tackle these types of attacks, such as, for example, the system alert window permission that an app needs to have to draw over other apps, notifications that are shown when this permission is in use, the possibility for apps to detect if an overlay is displayed and then to block touches, or default blocking of pass-through touches in most cases that were introduced a few years ago. The important takeaway from this slide is that all of the previous mitigations assume that the victim app is at the bottom of the backstack and that the malicious app is on top of the backstack and hides the victim app. So what is new about TapTrap? Assume that we have a malicious app that does not have any permissions at all. This malicious app can launch another victim app using an intent. For example, the Chrome browser that loads an attacker-controlled website, and this website immediately requests the camera permission. In this case here, we have a same task transition. That means that the browser activity and the attacker activity are launched within the same task. By default, all activity transitions are same task transitions. And for same task transitions, Android allows the launching activity, so in this case here, the attacker activity, to pass in a custom entry animation. And this custom entry animation is where it gets interesting. The animation is in full control of the attacker. And the attacker can, for example, pass in an animation that makes the new victim activity look like this here. In this case, the animation makes the victim activity semi-transparent. I did this on purpose so you can see what is going on behind the scene, But in a real-world setting, this animation could make the victim activity completely transparent so that only the underlying attacker-controlled activity is visible. The goal of this malicious activity, now similar to a traditional tap-checking attack, is to lure the user into clicking on a sensitive UI element, such as, for example, the allow button here. This works because even though the victim activity is completely transparent and only the attacker activity is visible, it is on top of the backstack. And because it is on top of the backstack, it receives user touches and previous mitigations do not apply. This animation that can be passed in also has some other nice properties. So first of all, we've already heard that it can change the opacity of the new activity, so it can make the new activity transparent, but it can also scale the new activity. So an attacker can, for example, zoom into the allow button until it spans the whole screen. And then it doesn't matter anymore where on the screen the user clicks, as every single click on the screen is redirected to the allow button. And the animation can last for up to 6 seconds, and after 6 seconds, the attacker can repeat the attack. What are possible implications of TapTrap? One possible implication is to attack system apps and dialogues. An attacker can, for example, lure the user into granting sensitive runtime permissions, such as, for example, access to the camera or to the microphone. Another implication is device erasure. An attacker can lure the user into granting the special device administrator permission. And with this permission, an attacker can erase the complete device. And then there are also some other implications on system apps and dialogues, and you can find more information on this in the paper. We can also attack the browser. So we've already heard that we can perform web permission bypass attacks, but we can also perform web clickjacking attacks. That means we can, for example, load a victim website in a Chrome custom tab, that means in a browser, for example, a shopping website, and then lure the user into tapping the Pay Now button. We analyzed 10 major browsers on Android, and we found that 8 of these are vulnerable to TapTrap. And then last but not least, we can also attack third-party apps. To assess the impact of TapTrap on third-party apps, we performed a large-scale analysis of about 100,000 apps from the Play Store. We say that an activity is vulnerable to TapTrap if it fulfills 4 criteria. First of all, an activity has to be externally launchable and it has to be same task launchable. We were able to check these criteria using a simple manifest analysis. Another criterion is that the activity does not override the custom entry animation. Because if an activity overrides an entry animation, then the activity would also override any animation that is passed in by the attacker. And then the fourth criterion is that the activity does not wait for an entry animation to finish before handling user input. And we checked the last 2 criteria using a bytecode analysis. And then we define an app as being vulnerable if it contains at least one activity that is vulnerable. In total, we found that 76% of apps are vulnerable to TapTrap, and 7% of all activities are vulnerable to TapTrap. So now we know about TapTrap and we know about the implication of TapTrap. The question that naturally arises now is TapTrap already abused in the wild? And to answer this question, we performed a large-scale analysis of about 100,000 apps from the Play Store. The animations that can be abused by TapTrap have to be declared in XML files in the Android APK. So we first decompressed each APK using APK tool to get its resources, and then resolved any references that these resources have. We then recreated the animation object that Android uses to run animations based on these XML files, and then ran the animations using Robolectric, and that is a testing framework. This allowed us to capture two properties of the new victim activity. First of all, the opacity, and second of all, the transformation matrix. We then used these properties to calculate two scores, a scale score and an opacity score. Both scores range from 0 to 100, and they quantify the potential of an animation to be abusable by TapTrap. So that means that if we have an animation that has a very low opacity over a very long time, we would assign this animation a very high opacity score. The first finding of our analysis was that animations can actually exceed the duration limit of 3 seconds. This is because of a bug in the implementation of the duration limit. While this is not a requirement for TapTrap to work, it increases the attack window and therefore makes the attack easier to carry out. Our second finding was that TapTrap is not exploited in the wild. We found that 28 apps had a scale score or an opacity score of at least 50, and we then manually analyzed these apps, and based on our manual analysis, did not find any malicious TapTrap behavior. So TapTrap is a UI-based attack, and we also wanted to find out how stealthy the attack is and whether users notice when such an attack takes place. Therefore, we conducted a user study in which participants played 2 rounds of a game that we developed and that we call Kill the Bugs. In Kill the Bugs, participants had to kill bugs that appear on the screen to advance to the next level. The game consisted of 3 levels, and in each level we used TapTrap for a different purpose. In the first level, we opened an attacker-controlled website in a Chrome custom tab, so that means in the browser, and this website requested location permission. In the second level, we did the same, but with the camera permission, and this is what you saw a few slides ago. And in the third level, we lured the users into granting the device administrator permission. Participants played the game twice. In the first round, they weren't aware of the real objective of the user study. And before the second round, we debriefed them and told them that the game is actually malicious and tries to lure them into granting specific permissions. In total, we were able to recruit 20 participants, mainly from entry-level bachelor courses at our university. Out of those 20 participants, all of them failed to detect TapTrap, even in the second round. So that means even after we've informed them that the app is malicious. And this shows that TapTrap is indeed a stealthy attack. So what are possible mitigations? Mitigations can be implemented by the Android system, by apps, or by the user. When we talk about Android can, for example, implement a strategy in which it ignores touches during an activity transition when the opacity is under a specific opacity threshold or the scaling is over a specific scale threshold. Unfortunately, as of now, even the newest Android version, Android 16, is still vulnerable. GraphineOS, which is a custom ROM for Android, however, has already fixed the issue. Also, apps can protect themselves. Apps can, for example, override the entry animation, or they can wait for the entry animation to finish before handling user input. And this is a strategy that the major browser vendors have implemented after we've reported the issue to them. And for users to protect themselves until a platform level fix is available, they can disable animations in the accessibility settings. This already brings me to the end. Thank you very much for your attention. Feel free to check out our website taptrap.click, where we have a demonstration video, where we have our analysis pipelines and also some more information.